to return, but before returning to our review of hypothesis testing, okay, we introduced it last week. Before returning to that, I just want to review confidence intervals again, because confidence intervals are kind of, in the way we generate confidence intervals, the idea of how many standard errors away from the mean we are, and how sample size affects the variability of samples means that we would take, and so on and so forth, or proportions for that matter. That's kind of key to our whole understanding of hypothesis testing for numerical variables. This is what we call the t-test. So in order to review this idea of confidence intervals for means and proportions, I put together an exercise. I'm going to open it here. You can open it on your computers as well. Whoops. Let me get this to resize a little bit. Okay, and this exercise is themed for the holidays. Let me get it to a good size. So we'll do it this way. So I step up a little easier. Okay, so it's Halloween. We're getting ready to get those little ghouls and monsters ringing our bell asking for trick or treats. And of course, a recurrent theme on Halloween is zombies. Okay, I'm sure you get plenty of zombies knocking on your door looking for candy. This season, there's a new movie, or a sequel to a movie called Zombieland, which is a pretty funny. The original was a pretty funny version of a zombie movie, but we'll see how funny this one is as well. Okay, so here's a zombie food pyramid. Now, a lot of you guys are nutritionists, so you will appreciate that. Of course, zombies, we know, love brains, right? So that's their primary, that's what they eat the most of. And then they eat livers, and they eat heart and lungs, and stomachs and intestines, and so on and so forth. And then bones and gristles, so as well. No carbs, though. They really don't eat very much carbs, zombies, right? So their primary food source being brains and spinal cords, high in protein, low in carbohydrates, basically a low carb diet. We might be interested in knowing what their serum cholesterol levels of zombies is. Okay, so we're gonna randomly measure the serum cholesterol in 25 adult zombies, randomly selected adult zombies. The mean sample is found to be 151.4, the mean total cholesterol value, and the standard deviation for these for zombies is found to be the same as for living humans. We're going to assume it's the same as for living humans, 38 milligrams per deciliter. Well, let me think what I'm looking at here. Okay, so we're assuming that we know the population standard deviation. The sample mean that we got of 25 randomly selected zombies was 151.4. Okay, so what is that? Now remember that we have a number of different ways to indicate what we're working with, for instance. Okay, so for instance, I could be looking at population mean, or I could be looking at population standard deviation. Notice I use Greek letters. Those are parameters. Okay, and on the other hand, I could be looking at a sample mean, which we indicate as X bar, or a sample standard deviation of the values, in this case, 25 values. That's a statistic. Again, this should be review basically for most of us. Okay, so in this case, we are told that we randomly selected 25 zombies and found the mean of the sample mean to be 151.14. So X bar is equal to 151.4. Okay, and on the other hand, we were told that we could presume that the population standard deviation, sigma, is equal to 38. Okay, so now we're asked, calculate a standard error for zombie cholesterol levels. Well, what's the standard error equal to? How do we calculate a standard error? Standard error is equal to the standard deviation of the population over the square root of the sample size. Standard error is the variability of repeated samples of that sample size. In other words, we took samples of size 25 over and over and over again. This is the standard deviation of those averages that we got from each time we took a sample of size 25. So that's our sample standard deviation, our sample mean standard deviation. Okay, so what is that? Since we know sigma, we're told sigma in this case, we can just calculate this, and it's 38 divided by the square root of 25, which is 5. So it's going to be 7 and 3/5 is 0.6. Okay, 7.6. Okay, I presume that that's right. Okay, so our standard error is equal to 7.6. So if I looked at this distribution of sample means, it would be something like whatever the population mean is, which we don't know, right? We only know X bar. And the standard deviation would be 7.6. And that would tell us that 95% of the sample, if we took a sample of size 25 and found the average, 95% of the time it would be between 1.9 standard deviations below the mean, 2 if we're using empirical rule, or 1.96 standard deviations above the mean. In other words, roughly 15 below the mean or 15 above the mean. Actually 15.4 above the mean or 15.4 below the mean, right? So we know something about the way samples are distributed in this, sample means are distributed in this population. So that allows us to determine a confidence interval for the mean that we calculated from the 25 sample of 25 zombies that we actually measured. And how do we do that? We say X bar plus or minus. Now we have to come up with a value here. Since we know the population standard deviation, we're going to use the value of Z for an alpha equals 0.05 for 5% chance of being outside of the our confidence interval. Okay, sometimes you'll see that as alpha over 2 is equal to 0.025, right? But it's the same thing as alpha is equal to 0.05. Or in other words, 95% certainty. In other words, 5% chance of being wrong, 95% chance that we're, I guess, right in a sense. Okay, not exactly the way professional statisticians might phrase this, but that's pretty much the idea here. Plus or minus the z-score that we need for our 95% confidence interval times our standard error. So in this case, what do we have here? We have 151.4 plus or minus, and z for when we know the standard deviation in the population and a 95% confidence interval, we know is roughly 2 standard deviations below and above, or more precisely 1.96 standard deviations above and below the mean that we got, times our standard error, which is 7.6. Okay, so let's do this calculation using our calculator. And I'll move it over. Whoops. Let me get the pointer. Move it over here, and let's see. 1.96 times 7.6 is equal to 14.89 or 14.9 roughly. What do we call that number, by the way? Okay, this is 14, whoops, let me get my pen back. 14.89, right? 151.4 plus or minus 14.81. Anybody want to answer to guess on what this number is called? This was a standard error, right? This was our z-score that we needed for 95% confidence interval. When we multiply them out, what is that called? We're adding and subtracting from that quantity. You guys remember? Marguerite, do you remember? It's called our margin of error. Margin, IG. Okay, margin of error. Okay, because we're adding and subtracting it, right? It's kind of our margin of error, plus or minus around that mean. Okay, so let's calculate out what our actual confidence interval is, right? And it's going to be 2 numbers. We're going to subtract that margin of error, and then we're going to add that margin of error to our sample mean. Okay, and let me get my calculator back. Oops, that's not what I wanted. And now I got to go back here, my pointer. Okay. There we are. Here we go. Okay, so I'm going to take that number and I'm going to add it to my memory and I'm going to clear it out. And 151.4 minus, and I'll recall that number, is equal to 136.5. So the number that the lower range of my confidence interval is going to be 136.5. Okay, now let's go back and get the upper range. 151.4 plus our margin of error is going to be 166.3. Okay, and 166.3. There we go. Okay, so that is our 95% confidence interval. So let me put you on the spot again. If I were to ask you, what does that mean? What does that mean to us actually, that confidence interval? What does that confidence interval imply about the mean of the population? Well, let's think about this. What this tells us that it is that we are 95% certain that the true population mean, mu, is between these two numbers. Now, what does that tell us about if I repeated this process 20 times? If I took 20 samples of size 25, 95% of the time, I would capture the true population mean between the two numbers that I calculate to be my confidence interval. And 1 out of 20 times, it's likely that the true population mean would be outside of my confidence interval. So if I did it 100 times, I'd probably capture the true population mean 95 out of 100 times and miss it 5 out of 100 times. So that's what this really tells us. That's what the confidence interval really tells us, but it's a useful tool. If I had just told you, for instance, completely separate from any other kind of information, if I had just told you that I took a sample of size 25 and I found that the mean of my sample was 151.4 and gave you no other information, you would have no idea how precisely, how much variability there was in this sample of zombies, or in this population of zombies. You would have no idea of how likely it is that the true population mean would be anywhere near that 151.4. But now, by giving you this confidence interval, 0.5 to 166.3, by giving you this confidence interval, now you have much more confidence about where the true population mean really lies. You know that you're 95% sure that it's within that range. Your sample came out to be 151.4, but you're 95% certain that while the sample doesn't give you the exact population mean, you know that this is 95% certain to give you the true population mean between those two numbers. So you have a lot more power. So now, what about here? I said, next thing I said, repeat this for 99 and 90% confidence intervals. Okay, and I'm going to give this a try. Okay, so now how would I go ahead and do that? Okay, so my formula for my confidence interval is x bar plus or minus a value of z for alpha is equal to 0.05 times my standard error. Okay, and again, my standard error, my mean was x bar was equal to 151.4. My standard deviation was equal to 38, and my standard error of the means is equal to I have a student, is equal to, I think I said 7.6, right? That would make sense, 5 into that. So the standard error is equal to 7.6. So now how would I calculate these other confidence intervals? We know that we use 1.96 to calculate our 95% confidence interval. And as we learned previous to this, that if we want to find our 99% confidence interval, we would use X bar plus or minus the value of Z that we would need for 99% confidence interval, which happens to be 2.58, times our standard error. Okay, so now why 2.58? Well, 2.58, if we go to our Z table, represents half of 1% in each one of the two tails in a normal distribution. The number of standard deviations away from the mean that we have to be for 0.5% each end, which would leave 1% total in the two tails, which would leave 99% of the outcomes in between those two. So we would use 2.58. Well, what does that do to our confidence interval? Well, that does to our confidence interval, since we're multiplying our margin of error by a bigger number, it's going to make this margin of error larger. So it's going to make our confidence interval wider. So that makes sense, doesn't it? In other words, if our confidence interval for 95% is this wide, if we make it wider, we can be more confident that the true population mean is between those two numbers. So we would expect our 99% confidence interval to be wider. So in this case, it's going to be 151.4 plus or minus 2.58 times the standard error, which is 7.6. Okay, and how about if we also look at our 90% confidence interval? Well, 90% confidence interval is going to be 151.4 plus or minus, well, in this case, the Z-score we're going to use is 1.64. Again, this is a smaller number, so what's going to happen with this? It's going to be narrower. So our 90% confidence interval can afford to be a narrower range, because we're saying that we can have less, we'll accept less confidence, that we're willing to miss capturing the true population mean 10% of the time instead of 5 or 1% of the time. So it can afford to be narrower. Okay, so that's going to be 1.64 times 7.6. So if we go ahead and actually do this calculation, okay, and I'm going to clear out memory. It's going to be 2.58 times 7.6 is equal to 19.6. I'm going to put that into memory. Clear it out first. I'm going to clear this 151.4 minus our margin of error is 131.8. $131.8 to, and get our calculator back again. Is equal to 171 even. It looks almost even. $171.0. Okay, notice that this is wider than our 95% confidence interval was. Now, what's our expectation for 90% confidence interval? It's going to be narrower than both the confidence intervals we calculated before. So let's give that a try. Okay, so I'm going to clear out memory, and I'm going to go 1.64 times 7.6 is equal to 12.4, a smaller number for a margin of error. I'm going to put that into memory. 151.4, oops, slight mistake, 151.4 minus our margin of error for 90% is 138.9. $138.9. Notice it's much narrower. And the upper range is going to be 151.4 plus our margin of error, 163.9, 163.9. Okay, that's our 90% confidence interval and our 99% confidence interval. Okay, so presumably, if you were to find yourself on an exam or on a homework assignment or something like that, if you were to find yourself with this same problem, what were the key elements that we saw here? The key elements were the sample size. We recognize immediately that it's a sample that we're dealing with, 25 randomly selected zombies. So so our mean is going to be X bar. Then we also noted that we knew the population standard deviation, an unusual situation, but in this case we knew the population standard deviation and we knew our sample mean. So we were able to calculate our standard error using the z-score and the sample size, right? Sigma over the square root of n, okay? And then we could use the z-score, 1.96 for a 99% confidence interval, 95% confidence interval, 2.58 for a 99% confidence interval, and 1.64 for a 90% confidence interval. You're able to use these z-scores in your formula for the confidence interval to calculate your margin of error and add and subtract it from your sample mean. So that's kind of a unique situation because that's what we happen to know about it. The mean of the sample, the standard deviation of the population, and the sample size, right? That sample size was the other thing that we knew, and we're able to calculate a standard error from that. Okay, so now the next problem is going to be very similar to this, except we're going to change one element, and it'll make some sense to you. Again, same population. If I can't click in here and get this to advance. Okay, in this case, we're going to repeat the study above, assuming the population standard deviation for zombie cholesterol is not known. So if we don't know, and this is really the situation we're in 90% of the time, if you don't know what mu is, and you don't know what sigma is, population standard deviation, what are you left with? You have to use your sample, size 25, you have to use your sample to estimate the population mean, and you have to use your sample standard deviation to estimate the standard deviation of the population. Well, this we're anticipating that we're gonna be estimating the sample mean. That's why we come up with a confidence interval rather than a single value. But now standard deviation, we weren't, when we looked at our formula for standard error, it was sigma over the square root of the sample size. It assumes that that the formula assumes that the standard deviation of the population. Well, in most cases, we're going to be more likely to be in this situation where we don't know that, and we can only estimate it from our sample standard deviation. So in that case, standard error is equal to the standard deviation of the sample over the square root of the sample size. That now introduces a bit more uncertainty, right? Where that's not as exact as knowing the population standard deviation. So in order to make up for that uncertainty, we learned that we use a t distribution instead of a z distribution. And for every sample size, the bigger the sample size is, the better we know, the better an estimate of the population standard deviation we have. So there isn't a single t table. There's many t. There's a t table just like there's a z table for every sample size, whether the sample size is 2, 3, 5, 100, 200. There's a separate table. But in order to avoid having separate tables, we only are interested in the critical values of t that we need to know to calculate our confidence intervals. So what are those going to be? Well, just as we saw now, most of the time we're going to be interested in a 95% confidence interval, right? So instead of using z which is equal to 1.96, we're going to use a value of t. That value of t is going to be dependent on the sample size. It's going to depend on how big the sample is. If I have a super large sample, 1.98, if I have a super large sample, then 1.96. If I have a super large sample, t is going to get closer and closer and closer to 1.96, but it'll never really reach 1.96 until you either are at a sample size equal to infinity or the entire population, in which case you know sigma. So that's why it's 1.96. Okay. So it's always going to be bigger than 1.96. If the sample size is small, that number may be pretty big. T might be, T for a 95% confidence interval, instead of being 1.96, T might be equal to 2.6, let's say. I'm making that number up for the moment. But if we get to a sample size of 25, maybe it's equal to 2.1. If we get a sample size of 100, maybe it's equal to 1.98. So it's getting closer and closer and closer to 1.96 as the sample size gets bigger. But now we substitute t for z in our confidence interval, okay, to make our confidence interval wider to make up for our uncertainty about the standard deviation in the population. So now our confidence interval is going to be equal to x bar plus or minus the value of t, right, for alpha equals 0.05. This is for a 95% confidence interval. Remember, also sometimes you'll see that as alpha over 2 is equal to 0.025, indicating each tail is 2.5, right? But then you have two tails, so it's really the same thing. And with our sample size of, in this case, with our sample size next, right? Well, in this case, our sample size is 25, but we don't show it as n equals 25. We show it as degrees of freedom equals 24. Okay, same idea, but we just use degrees of freedom instead. Degrees of freedom is equal to the sample size minus 1. Similar to the way we calculated the variance in the standard deviation way back at the beginning of the first session that we had, where we divided by n minus 1 instead of by n. So that's degrees of freedom. So the t-score for 95% confidence and a sample size of 24 degrees of freedom, times our standard error, calculated just as we did before, except that we don't know sigma, so we have to use the standard deviation instead. So I'm going to go ahead and calculate this for a 95% confidence interval. So it's going to be 151.4 times the t-value, I'm going to leave that as it is for right now, times our standard error, which is standard deviation was 38. We didn't change, divided by square root of sample size 5, which is equal to 7.5. That's just coincidental that it turned out the same. Our sample happened to be the same. Could have been different, right? Because the sample, if we took a sample again, the standard deviation might be different and the mean might be different. Okay, so what is this value of t going to be in this case? Well, that's a whole nother thing. Now we need to know what the critical value of t is, what that value of t is going to be for alpha is equal to 0.05 and for 95% confidence interval and degrees of freedom equal 2. And for that, we go to a t-table. Okay, and let me turn this off and see if I can't find it quickly. Okay, you should have this on Blackboard if you need to get to it. I'm just using this one I'm used to using. You can use any one that you want. I'm going to ignore the writing in the background. I don't want to erase that right now because I want you to be able to see it when we come back. So if you notice at the top here, this is the confidence levels, right? And this is the right tail probability. In other words, the right tail has 2.5%. Well, there's two tails, a right and a left. So the right tail has 2.5, left tail has 2.5. That's 5% area where we'd be outside of our confidence interval, right? And what does that imply? 5% outside the confidence interval, 95% chance of being inside the confidence interval for the true population mean. So this is the column we're going to use for a 95% confidence interval. And what is the number that I need to use for t, our critical value of t? So I'm going to go scroll down to a degrees of freedom is equal to 24. right? Sample size -1. I'm going to move over to that row. And here is that row, and it is a column rather, and it's 2.064. So the critical value of T for this situation, sample size of 25, 24 degrees of freedom, and 95% confidence interval is 2.064. See, if the sample size had gotten bigger, notice we'd be closer and closer to 1.96, like down here at 100 sample size of 100. So in our case, it's going to be 2.064. Let me get back to that. Degrees of freedom, 24, 2.064. Okay, so let me get this out of the way. So now let's go ahead and substitute that. This is 2.064. Okay, I'll pull up my calculator. And I'll clear this out, and I'll clear my memory. And I'm going to go 2.064 times 7. I'm sorry, that should be 7.6. 7.6, right? Remember, recall it was 7.6, I think. We calculated it before, is equal to 15.684. I think while we did it before, with Z is equal to 1.96, this came out to be 14 something. So now this is a bigger number. Our margin of error is a bigger number, which means our 95% confidence interval when we knew the population standard deviation is narrower than when we don't know it. And that makes sense because we need it to be wider to make up for that level of uncertainty. So I am going to clear my memory, and I'm going to put this into memory, and now I'm going to go ahead and calculate my lower and upper values. 151.4 minus my margin of error is equal to 135.8. Okay, that's going to be 135.8, and our upper limit is going to be, clear that out, 151.4 plus my margin of error, and that's going to be 167.1. There you go. Had we known what the population standard deviation was, we would have, in this case, we would have used 1.96 instead of 2.064. But since we don't know the population standard deviation, we only know the standard deviation is sample, we had to look up on our t-table what t-value we should use based on our sample size. Now, given all the information that we have given here, what if, given this information, you knew that what the mean was, you knew the mean for the sample was, you knew the sample standard deviation, but not the population standard deviation, and you knew the sample size, what would you have used if you needed to calculate a 99% confidence interval? Right, if we had wanted a 99% confidence interval. And what about a 90% confidence interval? Well, for that, we go back to our t-table. See if I still have it open. Nope, I'll have to dig it up, I think. There it is. Okay, here's our t-table. And for a 90, I'm going to actually clear this out just to make it easier to read this now. Okay, so for our 95% confidence interval, giving our sample size of 25, our 95% confidence interval, I'll scroll this up, our 95% confidence interval, or sample size 25, 24 degrees of freedom, was 2.064. That's what we used for T, multiplied it by the standard error. Well, what about if we wanted a 99% confidence interval? Well, in that case, Let's see, let's go back up to the top here. And here's our 99% confidence interval. And here's our 90% confidence interval. Second row and the second to last row. Okay, 90% and 99%. So I'm going to go back here to 24. There was our confidence interval for the t-value we used for a 95% confidence interval. Well, now for a 99% confidence interval, we would have used, for the same sample size, we would have used 2.797. And if we only needed to be 90% certain, this would be our 90% confidence interval, we would have used 1.711 and done exactly the same calculation using this as t for a 90% confidence interval, using this as t for a 95% confidence interval, and using this as t for a 99% confidence interval. So this would be the narrowest in between and the widest. As we want to increase our confidence that we capture the true population mean, we make our confidence interval wider. Okay, any questions about that? I'll hold on for a second while I give you guys a chance to maybe type into the chat box and ask a question or two before I move on to the next thing, which is also here in our warm-up. That's a Hunter graduate, by the way, that just came up on the screen. That's by the time you take statistics and all epidemiology, all these other courses, you're pretty worn out probably, right? Okay, so hopefully that's how they dress up for Halloween. That's not really what they look like at graduation. Okay, so based on a careful study of Night of the Living Dead and other zombie movies, it appears that zombies are predominantly male. A random sample of 100 zombies for Halloween weekend zombie movie marathons found that 58 of this sample were male. What is the point value for the proportion of male zombies? By point value, we're talking about basically when we're talking about numerical variables, we're talking about what's the average when we say point value. Okay, when we're talking about a binomial variable, two values, then we're talking the point value is a proportion. So 58 out of 100 of these zombies that we randomly selected were male. So our point value in this case is P, right? The prevalence proportion and so on and so forth, which is equal to 0.58. In other words, 58 out of 100 over 100. Okay, that's what P is equal to. Well, the only problem here is that P, right, refers to the population. We don't use a Greek letter, so that's the population proportion. We don't know that, right? We only know the proportion of the sample that we took of 100 zombies. Okay, so really I need to differentiate between P and P that I got from a sample. So I'm gonna, just like I use X bar to distinguish between the mean of the population and the mean of the sample, I'm going to use a cap to indicate that that's a sample proportion. So P cap is 58 over 100 rather than P, and we're just distinguishing between the population proportion and the proportion that we got from our sample. So now let's calculate a 95%. Well, it's very nice that we know that P cap proportion for our sample is equal to 0.58. But what we're really interested in is the entire population proportion. Since we'll never know that unless we watch every zombie movie ever made and counted every zombie, that's the only way we'll know that. And they're coming out all the time. They got 3 of them coming out this fall, this Halloween, and so on and so forth. You know, so who knows? Yeah, and I think I just saw the sequel to Zombieland, and there were about 1 million zombies in that. So counting them was, forget it. We never get done, right? So only thing we can have to work with is a sample, right? So our random sample of 100 zombies turns out to be 58% male. But that's very nice, but it's a sample size of 100. If I did it again, I would get a different proportion. Maybe I get 57, maybe I get 59. So I need to I need to use this information that I have to describe how well I know from this proportion and this sample size, how well I know the true population proportion of zombies, of the zombie population. Males, how many males and what proportion of zombie population is really male, the entire population, right? So again, I need a confidence interval. I need to know that this is P cap, but I also need to know what the 95%, in our case, 95% confidence interval is for the zombie population. Well, just like means, just like our point estimate for a numerical variable, the cholesterol, the mean, we're going to find a confidence interval for P cap. So what's the confidence interval going to be? What's similar to our other point estimate? P cap plus or minus a value. Okay, this could either be T or Z, right? Depending on if we know the population standard deviation or if we don't, and the sample size, for instance, okay, times our standard error. Well, I'm going to make things simple for you, because when we do this kind of survey, we're usually dealing with large samples, 100, 1,000, and so on and so forth. We're going to assume that we know the population, standard deviation. Okay, in a sense, we know how to calculate it. We can use Z instead of T, right? So for a 95% confidence interval, for Z, I'm going to use 1.96. So our population proportion that we got from our sample is 0.58 plus or minus 1.96, because we're going to be dealing almost exclusively with very large sample sizes, 1.96 times our standard error. Well, what's our standard error going to be equal to? This is a bit different than it was before. Our standard error is going to be equal to the square root of P cap in our case, because we don't know what P is, times 1 minus P over our sample size. As the sample size gets bigger, standard error becomes smaller, which is what you would expect. We know our variability with a bit more precision. Okay, so what's our standard error going to be equal to in this case? It's going to be the square root of 0.58 times 1 minus P, which is 0.42, over the sample size, which is 100. In our case, I stuck with a small sample size. Really, in real life, you probably would be working with larger sample sizes to have at least somewhat more confidence that you could do this. Okay, so let's do that for our standard error. Okay, so I'm going to clear out my memory, and I'm going to say 0.58 times 0.42 is equal to 0.24 divided by 100. Oh, oops, I'm going to have to do this again. 0.58 times 0.42 equals divided by 100 is equal to this, and I'm going to find the square root of that. That's equal to 0.0549. Okay, I'm going to write that down. Equals 0.049. So now, I'm going to take that standard error and I'm going to put it into my formula for a confidence interval, 0.049. So now let's calculate what our margin of error might be. Okay, so 0.49 times 1, whoops, I need to get my pointer back, times 1.96 is equal to 0.096. So I'm going to clear this out and I'm going to put this into memory. And I'll clear. So this is, let me recall that just so I have it, 0.97. So this is equal to 0.97. 0.97. Okay, so 0.58 plus or minus 0.97 and 0.097, and we'll calculate that, get our confidence interval. I'm actually going to use the real numbers since I saved them in my calculator. Okay, so I am going to clear this out, and I'm going to put this into memory. Oops, again, I got to get my pointer. Clear and put this into memory. I'm going to clear this out. 0.58 minus my margin of error is equal to 0.48, 0.483, 0.483, and my upper limit of my confidence interval I'll clear it out, 0.58 plus my margin of error is going to be equal to 0.68, 0.677. 0.677. So, although I found my margin, the proportion of male zombies in my sample was 58% or 0.58, I found that my 95% confidence interval, I'm 95% sure based on this sample size of 100, that my true population proportion is between 0.483 and 0.677. Well, that's very interesting, because now if I'm concerned about what's the likelihood that there's more males than female zombies, I want to show that there are more than, that more than 50% of the zombies are male, right? Like this guy over here, right? Well, in this case, I'm 95% sure that the true proportion is between 48% and 68%, right? So I'm not really 95% certain that it can't be 50%, because 50% is within the interior of this confidence interval. It could be 50%. And the only way I would be more than 95% sure that it isn't, it would have to be outside the confidence interval 50%. So in this case, my confidence interval doesn't allow me to say with 95% certainty that the true population proportion is different than 50%. Okay, so now if we wanted to repeat this for 99 and for 90%, what would we do here that would be different? The only thing we would do that's different is for our Z value. For 99%, we use 2.58, and for 90%, we would use 1.64. And again, 1.964, 95%, 95, 99, and 90% confidence interval. Okay, so again, I'll pause and give you a chance to, if you have a question, to ask a question. Okay, how are you doing back there? Is that okay? Does that make sense to you?
Yeah,
Okay, good.
you know, actually, the test I'm doing is a lot of questions about the mean, medium, null hypothesis, and stuff like, you know, that was most related to what I was learning from you.
Oh, okay, good. Excellent. All right.
A little coincidental.
Okay, good. I'm glad you're listening in. Okay, so at any rate, so now I'm going to move on from here, because now we're going to take this idea of looking at how many standard errors apart values are to make judgments about how likely that point values for groups are the same or are different. And we're going to start with something that's very similar to what we just did with the confidence interval, and this idea of testing this idea is 50% inside that confidence interval or outside that confidence interval. And that's going to be called a single sample t-test. Okay, and I believe we started talking about t-test last week, towards the end last week, and we know that the student's t-test is a method for evaluating a hypothesis that we would make. So let me just open this up. Let me open up, let's see, paired sample t-test, okay, let me open this up. Okay, here's a document that's on Blackboard. Single sample hypothesis test. Actually, this is a exercise sheet for single sample hypothesis test, two sample hypothesis test, and for paired samples hypothesis test, or proportions also, and for paired samples hypothesis test. Okay, so I am going to start with a single sample hypothesis test. Okay, so this is a sample of 9 people from a population. The values that we got, that we measure for each person's population, 5, 7, 8, 9, 10, 11, 12, 13, doesn't look exactly normally distributed, but that's okay. We're going to assume that it is. Okay, this is a central limit theorem allows us to generalize as the sample size gets larger to be not so concerned about how normal the original population is. Okay, so larger sample size becomes the less that we have to be concerned about how normal the original population is. Our sample distribution, as the sample size gets bigger, our sample mean distribution becomes more and more normal with the large sample size, even if we don't have a perfectly normal population distribution. Okay, so from population A, we have this result, these numbers. Okay, and sample size is 9. Sigma, the standard deviation, is known to be 3. Again, that's not something that usually happens, right? Normally, we don't know, we don't have a situation where we don't know what mu is, the population mean, but we do know what sigma is. That doesn't come up very often. Usually, we don't know either one of them, okay? Sample size 9, sigma is equal to 3. Okay, so I may have, did I put up a, yeah, I did. Okay, let me pull this up. I'm going to open up the Excel file that contains these values. Okay, here's the Excel file that contains these values, right? Same numbers that we have over there. Okay, these are all values of X. And let me cancel it. Okay, good. So now I'm going to take a look at this, but before I do that, I'm going to go back to my page here. And I'm going to scroll up just a little bit. And I am going to create a hypothesis, right? Well, what is our situation here right now? Let me get a less jarring color here. Let's go with blue. Okay, so what's our situation here? What is it that we want to show here? I'm gonna go down here. I'm gonna say, well, we have two populations here. Population A and another population with a known mean. I'll call that population B, right, with a known mean. So I have population A, for which I'm working with a sample. So I can find X bar, the sample mean, and population B, where I know what mu is. I know what the mean of that population is. So I want to say to myself, well, gee, how can I show that the mean of population A, not the sample mean, but the true mean of population A is different than the true mean of population B? Okay, in other words, that there's a difference between these two populations. Well, that's going to be what we call our null hypothesis. Our null hypothesis always starts out with an equality. So in this case, we're going to say our null hypothesis is that the mean for population A is equal to the mean for population B. Well, in this case, I know that the mean for population B is equal to 8, right? And the mean for population A, I don't know. right? It's just, I just have a sample, so I don't actually know that mean. Well, then I'm going to create an alternative hypothesis. Our alternative hypothesis is that the mean for population A does not equal the mean for population B, that they're different, the means are different. So I'm going to put does not equal, in this case, 8, because I know what the mean for population B is. So instead of putting the mu, I'll just put the 8. So here's my null hypothesis, and here is my alternative hypothesis. So my objective here is usually to prove that two groups have different means. So for instance, that a drug will lower blood pressure versus a placebo. In other words, the mean blood pressure for people that take the drug is lower than the mean blood pressure for people who take the placebo. I don't care about the mean blood pressure for people in the sample who take them versus people in the sample who don't take the drug. I want to know about the populations. I want to generalize it, not to just the people in the sample, but the people in the entire population. So I need to prove that. I need to show that it's unlikely that the null hypothesis is true, so that I can reject it and say it's not true and accept the alternative hypothesis, okay, which is that there's a difference in the mean. So that's my objective, really, is to reject the null hypothesis and accept the alternative hypothesis in its place. But now, in order to do that, I have to find the evidence to do that. And how do I do that? Well, the mean, I don't know the mean for population A, but I do know the mean for the sample from population A, and I know the sample size that I drew from it. Okay, and so in this case, I also know the standard deviation is equal to 3. So now I have to say to myself, okay, how can I show how, if these are different enough that I can reject my null hypothesis? Okay, well, the way I'm going to do that is that I am going to demonstrate that this value for population B is so different from the value for population A that if I looked at it from the perspective of a couple of distributions, that the two values would be more than 2 standard deviations apart, or in this case of the sample, 2 standard errors apart. In other words, I want to make sure that they're outside of the confidence interval of each other, right? So in this case, I'd be looking at mu A. I want to show that my mean is outside of the confidence interval, that my true mean for population B is outside of the confidence interval for my sample that I'm taking. Okay, I'm still, remember, I'm up at the top here where sigma is known. Okay, so let me go ahead and actually calculate that. So I'm going to clear this out. I'm going to go back. So I'm going to bring up Excel again. Because I want to do it in Excel because I'll save a lot of aggravation if I do it in Excel. Whoops. Take me a lot less time to do it in Excel. Okay, so what is X bar? X bar. X bar is equal to the average of all of these values. This is my sample. Okay, and N, what was the sample size? The sample size I can see right next to me is 9. And now, what is the standard deviation? What is sigma? I happen to, in this beginning, know what sigma is. Sigma is equal to 3. So if I know what sigma is, I can calculate the standard error, right? Remember, we're kind of like on the same track as confidence interval. The standard error is equal to sigma divided by the square root of the sample size, which is 9. But the square root is 3. So that comes out to be 1. In other words, 3 divided by 3 is equal to 1. So what does that tell me? Well, now I could calculate a confidence interval for X bar and see if the other population is within that confidence interval or outside of that confidence interval. That's one way I could approach this. But in reality and statistics, we take a different track on this. We calculate a p-value, a number of standard errors apart. In this case, since we know the population standard deviation, we're interested in a z value. So if I had told you at the beginning of this, as I did, that alpha is equal to 0.05, in other words, our tolerance for a type 1 error is 5%. I want to be 95% certain before I kick out the null hypothesis, right? And I only want to have 5% chance of being wrong. My alpha is equal to 0.05. Well, when I know the standard deviation of the population, as we've been told here, I use the z value for 95% or 1.96. That becomes my critical value for z. So now I want to calculate how many standard errors, how many z's apart are these two values. And how do I calculate that? Well, that's going to be z is equal to x bar plus or minus, x bar, here, x bar minus mu, the difference between the two of these. I'm going to see how far apart they are, right? The difference between the mean we know and the mean of the population we found from the sample. The difference, how many standard deviations apart are there? And I'm going to divide that by the standard error. And that'll give me the number of standard errors apart, the number of standard deviations or standard errors apart. In other words, how many z-scores apart are they? So let's calculate that. It's equal to x bar is this minus 8 over 1. I'm going to put this in parentheses to make sure it works right. I want that to work first. And it comes out to be 1.88 standard errors apart. What was my critical value of z? My critical value of z was 1.96. So in order to be 95% sure, less than 5% chance of being wrong, I would only reject the null hypothesis if these two values were more than 1.9 standard deviations apart, standard errors apart. Turns out they're 1.88 standard deviations apart. So I fail to reject my null hypothesis. Okay, so now what if I had told you that the standard deviation, sigma, is known to be 2? Oops, I can't change it. There we go. What if I told you it was known to be 2? Let me get this back. So sigma is going to be equal to, sigma is equal to 2. My standard error then is equal to 0.667, okay? So less variability in our population. It's equal to 0.667. Okay, so what would be the number standard? Okay, x bar minus mu, okay, 9.88 minus 8, the difference between the two, over the standard error. Well, this time the standard error is going to be equal to, 0.6667. Well, in this case, the t-score, the z-score is 2.8. These two values are 2.8 standard errors apart. So I can say with 95% certainty that the population means are different. In other words, I would get this big a difference in standard errors. These values would only be this far apart less than 5% of the time if the null hypothesis were true. I would only get an outcome with these two numbers, the sample mean and my other population mean. I would only get this big a difference given this standard error, this big a difference less than 5% of the time, which means that I can assume that I can reject my null hypothesis and be wrong less than 5% of the time. Really, statisticians look at it more as the description being that there's less than 5% chance that you get that outcome, which means you can reject the null hypothesis. Okay, so if this is bigger than 1.96, our critical value, you can reject the null hypothesis. Well, okay, so now what happens now? What happens if I don't know what sigma is? That my standard deviation has to be based on these numbers here, on my sample. Let's see what happens in that case. In that case, I'm going to copy these down so I can get started again. See what happens in that case. Okay, so now x bar, oops, X bar is equal to average. We haven't changed anything, so it's going to come out the same. Okay, and our sample size is still 9. And our, well, sigma, well, we don't know it's sigma, so I have to calculate the standard deviation. So the standard deviation, since we don't know what it is, we have to base it on our sample. Okay, so the standard deviation of our sample is 2.93. So now, okay, so our standard deviation of our sample is 2.93. So now I'm going to calculate my standard error. So what's my standard error going to be equal to? It's equal to sigma over the square root of n. Oh, but wait a second. I can't use sigma because I don't know what sigma is. I got to use the standard deviation. It's going to be equal to the standard deviation, which is less precise than knowing that. Oops. Standard error. Okay, let me redo this so that we can have it in the same column. So the standard error is going to be equal to standard deviation divided by the square root of the sample size, which is 9. Okay, it's going to be equal to 0.9781. Okay, so now, okay, it's very good. So now let's take a look at how we're going to calculate the how far apart that these values are. Well, again, it's going to be the value. Now, in this case, I don't know what sigma is. Right? Sigma is a question mark. So I have to, instead of using the Z table, I need now to have to use the T table. Why do I use the T table? Because I don't know the population standard deviation. So in this case, we're going to calculate a T value, number standard errors apart that these are, but I'm going to call it a T value instead of a Z value. So the T value is going to be equal to, just like before, 9.89 minus the value of the mean, 8, divided by, let me put this in parentheses first, divided by my calculation for the standard error, which is this value. Okay, and that comes out to be 1.93. So now the question is that big enough for me to reject my null hypothesis? Well, the way that we decide that, we need to know if it's bigger than the critical value of T. Well, what is the critical value of T? The critical value of T is the value of T that we get for that sample size and 95% certainty. So let's go take a look at Agresti again, if I still have it open. Nope. I'm gonna have to dig it up again. Okay, here we go. So for a sample size of 9, 8 degrees of freedom, our T value, or critical value of T, is 2.306. So our critical value of T critical is 2.306. So in order to reject our null hypothesis, right? Remember our null hypothesis? I erased it right now. Remember our null hypothesis was that the two means are equal. In order to reject that and accept our alternative hypothesis that the means are different, we have to see that they are at least 2.306 standard errors apart. Well, they're only 1.93 standard errors apart, right? So since this is smaller than our critical value of T, the two values are too close together, we fail to reject the null hypothesis. So we had 3 outcomes here. The first outcome was when we knew sigma, but we failed to reject the null hypothesis because they were we found the Z was our critical value, 1.96, but it wasn't big enough. And then we took another look at it with a sigma known as 2 instead of 3. And in that case, we did exceed 1.96, or a critical value is Z. Okay. And then in this case, where we were working with a sample, our critical value for T instead of Z, because we don't know what sigma is, population standard deviation is, and we have to use our sample to estimate it, right? Our critical value for T was 2.306. And when we calculated it, found the average and divided by, found the average, found the difference between this and the other population, 8, 9.8 minus 8 is 1.8, and divided by our calculation for the standard error, which was standard deviation of the sample over the square root of n. Right? When I divided by that, it was only 1.9 standard deviations apart, not the 2.3 standard deviations apart that I needed in order to reject the null hypothesis. Okay, so that is our single sample t-test. The 8 came from, question, thank you. The 8 came from the second population. The 8 was the mean for population B. In other words, keep in mind, we're comparing the means of two populations. In other words, again, I'll write the null hypothesis and our alternative hypothesis. Our null hypothesis is the mean for population A is equal to the mean for population B, and our alternative hypothesis is the mean for population A does not equal the mean for population B. So population A, we're told, is equal to 8, right? That's equal to 8, right? Population A, we don't know what it is, but we have a sample, so we can calculate X bar, right? So that's where we got the difference. That's where we're estimating what the mean for population A is. We know what the mean for population B is. That's why this is called a one sample t-test, or you can also call it a one sample hypothesis test. Okay, makes sense? So that's really what's going on here. Okay, it's just a single sample. A little bit less common than what we're going to do next, right? But this is easier to explain. This is a simpler way of looking at it. And that's the procedure that we would go through to solve this kind of problem. Okay, so now I'm going to clear this out. And unfortunately, we're not always going to be looking at single sample hypothesis tests. Often, we will be looking at two different samples. In fact, more often than not, we would be looking at two different samples. Okay, so let's say whatever these scores represent, we broke this up into two. We randomly sampled 9 males. Is it 9? Yeah, there's 9 values there, and 9 females. But you know, before I do that, I just want to show you one other thing. On Blackboard, you will find that in addition to the Excel files, I also gave you the same data in a SPSS file, single sample test.sav. I'm going to save that to my desktop. Okay, let me go back to the desktop. I'm going to save it to my desktop, and I'm going to go to the desktop. Oops, if I can get to it. Okay. If I can't find this easily. See where it wound up. There it is. I'm going to open that up. You'll see it's the same data that we had before. Oh, you know, it may open the wrong version of SPSS. Yeah, I got to stop that. That one doesn't have a license, so license is expired. That version, I got to go back to my older version. Let me get that to quit. Okay, so let me go here, and I will open SPSS from here. IBM SPSS version 25, and here it is right here. I need to install that other the newer version. I need to install because I don't have a license for it anymore. Every time I start it up, the newer version, every time I try and open from a file, the newer version takes over. Okay. Okay. So here's our data set, I think. Oh, no. Hang on, I got to open it. File, open data. I'm going to navigate to my desktop. And there is our single sample test. I'll open that, and we'll see those numbers up here. The syntax window describes what's happening, and here are our values for our our sample of 9 people in our population. So now I'm going to do the same thing that we did before, except I'm going to use SPSS to do the entire calculation. So I will go up to Analyze. Of course, before you do this, you would set up on paper your null and alternative hypothesis. You want and determine what your acceptable level of error is, what alpha is. I'm using 5%. You might want to use 1%, be 99% certain, right? In which case you would use a different t-score to compare, again, the different critical value with t. So I'm going to go up here to Analyze. I'm going to go to Compare Means, because that's what I'm doing. Compare the means of 2 populations. In this case, a sample and a population. 1 sample t-test, only a single sample. I'm going to move the sample that I'm interested in working with into my variables box. And then I'm going to put into the test value the value of the mean for the population that I know, 8. So what this is going to do, it's going to compare the mean of my sample, X bar, to the mean of the known population, mu for population B, which is 8. And I'm going to click OK. I don't need any options on this. I'll just click OK. And what does SPSS gives us? It gives us a 9 valid numbers, 9 valid sample. The mean was 9.89, just as we found before. The standard deviation was 2.93, and the standard error was 0.978. In other words, it did the calculation not knowing what the population standard deviation was, literally giving us the same values that we got when we did it manually using Excel. Okay, so now let's calculate what our t-value is. Well, let's go down here. Our t-value turns out to be 1.931 with 8 degrees of freedom. Sample size of 9 means 8 degrees of freedom. At this point, we could do 2 things. We could go to our t-table, okay, and I don't think it's open anymore, is it? No, it's not. Never there when I need it. Okay, Agresti. Okay, we could go to our t-table and look for 8 degrees of freedom and go across, and our critical value is 2.036, and then go back to our output for SPSS and look at it and say, oh, well, this is less than 2.036. It does not exceed the critical value that we need for the distance between these 2 means. So it would mean that we fail to reject our null hypothesis. Well, actually, SPSS goes 1 step further. It actually collects, and not only, instead of showing you, comparing this directly to that, the critical value for that particular sample size, what it does is it gives you a probability. This is significance or probability, same thing. The significance, 2-tailed, meaning our hypothesis is not one is greater than the other, but it's just equal or not equal. In other words, we're not making a prediction about whether the 2 means, whether population A is bigger or less than population B, only that it's different. That was the line we put through the equal sign, only that it's different. So that makes it a 2-tailed test. Could be on either side of population B, either lower or higher, but we're not prejudging that. Okay, so the significance, the probability that you would get this big a difference, this number of standard errors apart, if the null hypothesis were true, is 9%. Well, let's see. That's how likely it would be for you to get this extreme of value. Well, we don't want to reject the null hypothesis unless there's less than 5% chance that we would get this big a difference between those 2 means. In other words, that extreme a difference between the 2 of them. So since this is less than 5%, we fail to reject the null hypothesis. So anytime that your t-score is less than the critical value that you need, you're also going to find that your p-value or significance is going to be greater than 5%. So you're only going to reject the null hypothesis if your significance or p-value is less than 5%, and it's going to happen at the same time, your t-value is greater than the critical value of t. You don't, if you see this is less than 5%, you don't need to go to the t-table to check the t-value, because it will be greater than the critical value for this degrees of freedom if this is less than 5%. So all you need to look at here is this. Okay, are we okay with that so far? Let me get this out of the way so I can actually look to see if there's any comments. You guys comfortable with that? That you'd be able to do that in SPSS if you needed to? Okay, so I'm going to move on. I'm going to move on to what's a little bit more realistic. And I'll tell you what, I'm going to take a quick break so I can drink something and clear my voice out a little bit. I'm going to take a quick break, no more than 5 minutes, and then I'll be right back. And we're going to look at 2 sample t-tests. In other words, we're taking a sample of one population and a sample of another population and comparing the 2 means of our samples so that we can tell whether or not we can predict whether the means for the 2 populations are different. In other words, we're extending our hypothesis testing a bit more. So let's pause for just 5 minutes.
This conference will now be recorded.
Okay, we're back recording again, and we're back online again. If you have any questions, just type into the chat box. I'm going to move on now to looking at going from one single sample t-test to situations where we have 2 samples. So I am going to pull back up this document. And in this case, we have 2 populations, males and females. So before I do anything else, when you design a study or when you start a statistical analysis, you don't want to bias it. So I'm going to establish my null and my alternative hypothesis and my requirements for how what level of certainty that I want before I go any further. So I'm going to say my null hypothesis is that the mean for males is equal to the mean for females. And I'm going to say my alternative hypothesis is that the mean for males does not equal the mean for females. Now, this is called a 2-sided test. It's 2 sample t-test, but it's also called a 2-sided test. You might have noticed that in SPSS that it said significance 2-tail. And the reason for that is we're not prejudging whether or not that the mean for males is greater than the mean for females, or the mean for males is less than the mean for females. We don't care about that. We just want to know if it's different. So we're not going to prejudge that. Okay, you could do a single sample t-test where your null hypothesis, your alternative hypothesis might be that the mean for males is greater than the mean for females versus the mean for males is equal to or less than the mean for females, right? That's a one-tailed t-test. In other words, you're only going to reject the null hypothesis if you prove this to be true. You would only use a one-tailed hypothesis if you knew that there was no way at all that the mean for females could be less than the mean for males. I mean, greater than the mean for males. Okay, in other words, there's some physical reason why you would not get that outcome. Okay, so I'm not, for the most part, we're going to stick with 2-tailed tests, not prejudging which is greater or less than the other. Okay, so what are we going to do here? Well, we are going to take our 2 means. Okay, now we don't know the mean for males, and we don't know the mean population mean for females. We're left with just knowing the X bar for males and X bar for females. Hence, we have 2 sample results. We don't have 2 means. So how are we going to calculate what our value is going to be, whether or not we can reject the null hypothesis? Well, we're going to need to know what the t-value is for the difference between these 2 males. And that's going to be equal to X bar for males, or I could have done it the other way around, minus X bar for females. The order doesn't really matter, divided by the standard error. Now, what's the standard error? The standard error is the standard deviation, and we don't know what the standard deviation, we don't know what sigma is for males, and we don't know what sigma is for females, right? So we're going to have to use the standard deviations from these samples. So it's going to be the standard deviation divided by the square root of the sample size. And that's what's going to go down here. Now, the next problem is that, well, what is the standard deviation? I don't have one sample like I did before, and I just take 9 numbers, find the standard deviation. I have 2 different samples. Well, gee, what am I supposed to do now? Which of the 2 should I use? Well, let me think about this. Maybe I'll just use both. Maybe I will pool them together into a single standard deviation for 18 values and use that for the standard deviation. And we can do that. We're allowed to do that. We're only allowed to do that if we assume that the 2 groups have equal variances. That's a sticky thing to assume, right? We can imagine. So assuming that these 2 groups have equal variances, we can then pool the 2 standard deviations together and calculate a standard error, divide by the square root of n, use that standard error and use it down here to find what our t-score is. And what's our t-critical going to be? Well, now we have a sample size of 9 here. We have a sample size of 9 there. So what should I use for degrees of freedom? Well, as it turns out, we add them together, n plus n2, and then we're going to subtract 2. So in other words, we use 18 minus 2, but you would use 16 for our degrees of freedom. Well, I need a sheet with rules, don't I? I need to know, how am I going to remember all this? Well, okay, well, I'm going to go back to Blackboard. Okay, so let me go back to Blackboard. Whoops, let me leave that up here. And here we are. And if you go back to Blackboard, you will see, I'm going to erase this for now. Go back to Blackboard, I am going to see that there is a sheet here that I call t-test variations. Okay, so here is our standard, our t-test for comparing the means of 2 populations using hypothesis testing, in other words, a t-test. This is what we would do if we would use equal standard deviations. 2 populations or 2 samples are assumed to be equal. 2 populations assumed to be equal. So if the standard deviation of 2 populations are equal, we would state our null and alternative hypothesis. We've done that. Mu for group A is equal to mu for group A is not equal to mu for group B, males and females in this case. And then we would, if we can assume equal variances, and we'll come up with a rule for that in a second, we would first calculate a pooled standard deviation. This is basically a weighted average for the 2 standard deviations. It's going to be the sample size of group 1, 9 minus 1 is 8, times the standard deviation squared, the variance basically, of group 1 males, plus 9 minus 1, 8, times the standard deviation for females from that sample squared over n plus n1 plus n2 minus 2. I would work that all out, and that would give me my pooled standard deviation. And then I would use that under in the bottom half of this this fraction, in the denominator of this fraction, I would use the pooled standard deviation times the square root of 1 over 9 plus 1 over 9, the sample sizes. And this would represent my standard error. Okay, so here's the difference between my 2 means divided by my standard error. Boy, it's getting complicated, isn't it? Okay, and then I would then calculate my t-value. In other words, the mean for group 1 minus mean for group 2 over my standard error, give me a t-score. And then I would go to my t-table and determine what my critical value is. Well, in order to use the t-table to determine what the critical value is for 95% confidence or an alpha of less than 0.05, I would have to know what the degrees of freedom are. In this case, when we're assuming equal variances, we would use a degrees of freedom of n minus n1 plus n2, sample size 1 plus sample size 2, 9 plus 9 is 18 minus 2 is 16. I determine what the critical value is for 16. Degrees of freedom equals 16. Critical value is going to be 2.12. And then I would calculate my value of t and compare it to my critical value, 2.12. If the value of t I calculate is bigger than 2.12, I reject my null hypothesis and accept my alternative hypothesis. If it is not bigger, I fail to reject my null hypothesis. So we could do this by hand, right? That's perfectly okay, right? So now, what about if the variances are not assumed to be equal? Well, when would I assume the variances to be equal or not equal? Well, one of the rules, simple rules that you could use, for instance, in our problem here, one of the rules you could use is to say to yourself that, let's see, what will I do here? Okay, I'm going to calculate standard deviations of these two groups. And in fact, I have the Excel file. I'm not going to go to it right now. I would calculate the standard deviation of each of these two groups. Well, why not? Let's go to the Excel file. Okay. And I'm going to calculate standard deviation of each of these. Standard deviation for male sample is 2.7. Standard deviation for female sample is 1.9. Okay, so now I'm going to look at these two. And I got to make it determined. They're never going to be the same. They're always going to be somewhat different. So as a shortcut, what we might do is we might say to ourselves, if one of these is not twice what the other one is, I'm going to assume equal variances. If one of them is more than twice what the other is, I'm going to assume unequal variances. That's really kind of a rough way of doing this, right? When we use SPSS, we'll be able to use a test that gives us a more elaborate version of this estimate. But for our purposes, we're going to say that the means of the the standard deviations of these two populations have equal variances, have similar standard deviation. Okay, so that I will go ahead and use those formulas that I had in that first page. So now, and let's see, tell you what. Let me see if I can't pull that up here again. Where did I put it? Let's see. I don't see the Word file anymore. Let me open it up again. There we go. Okay, so let's say I was going to do this for the problem that we just had. Let me get this out of the way. Minimize that. And I'll minimize this. And where's my Excel file now? Okay, here's my two groups. Let me just try and get these set up so I can see both at the same time. Okay, so I'm going to calculate my pooled standard deviation. Okay, well, I'm going to do it in a few steps just to make it a little easier. So this top part over here is going to be equal to 8. And this is going to be equal to 8, this area over here. Okay, so now I'm going to take the standard deviation of this group, put it here. Then I'm going to take the standard deviation of the other group and put it there. So now, in order to finish the top, I'm going to say that this is equal to 8 times the standard deviation, 8 times the standard deviation times itself. That's going to be equal to 60. On this one, it's going to be equal to 8 times the standard deviation for group 2 times the standard deviation for group 2 squared. Okay, so now I'm going to add the two of them together. The sum of these two. Okay, so that's going to be, top part of this is going to be that number, and the bottom part is going to be 18 minus 2 is going to be 16. So I'm going to divide this top part of the that fraction by 16, and then I'm going to find the square root of it. So the pooled standard deviation is 2.37. Okay, and if you checked it out, if you looked, you can kind of see it's the weighted average. It's like really just the average of these two because the sample sizes are the same. But if the sample sizes were different, it'd be the weighted average of those two. Okay, so now I'm going to calculate my t-value. My t-value, well, actually, I have my means down here. No, let me get my means. Okay, average for males, average for females. I may have this set to hold numbers here, so it may actually be, oh, no, maybe not. Okay, so let me calculate my t-score. My t-score is going to be equal to the difference between these two means on top divided by my standard error, which is going to be this number. It's 1.029. My critical value of t was 2.12, I think. I don't remember. I think it was something like that, right? Does my t, the t that I calculated, does it exceed my critical value of t? The answer to that is no, so I fail to reject my null hypothesis. I'm going to repeat this calculation using SPSS. Okay, let me find my SPSS. Okay, so I'm going to open my other, I have to save it to my desktop first. Oh boy, a lot of windows open. Nope, that's not what I want. I need, nope, that's not what I want either. I don't even know I have that open. Okay, here we go. Okay, good. So I'm going to go back over here and let me save this. I'm going to take the SPSS version of this. Oh, maybe it'll open. Who knows? Hopefully it'll use the version I have open. No, it's not. Let's see which version it uses. I got the wrong version again. I really need to delete that. Okay, let me save it to my desktop. As a matter of fact, I'll save both of these to my desktop, that one. And I'm going to save the next one. Okay, let me make sure that that really saved. I did, okay, good. Okay, so now I am going to open that file, open data, and I'm going to open my two sample t-tests with equal variances. Same numbers we just worked with in Excel. And I'm going to go up here to, and notice it's formatted differently. I have two variables, the gender, which is male for one. I can actually flip on these value labels and flip them off. Okay, if I go to the variable view, you'll see that gender is listed as a nominal variable. And I noted that one represents male, one represents female, two represents male. And the values themselves, the variable name values, is actually a numerical or scalar variable. Okay, so I'm going to go here and I'm going to turn the value labels on so you can see what they are. going to say analyze, compare means. I'm comparing the means again. Independent samples t-test, in other words, 2 samples. And this time I'm going to put the values into my test variables, and I'm going to move gender into my grouping variables. In other words, what are the 2 groups that I want to compare? What 2 populations do I want to compare? Well, females were defined as 1, males were defined as 2. I'm going to click OK, and SPSS will open up the output window again and perform our independent samples t-test. So let's see what we wind up with. And I must have made a mistake on the Excel. Let me go back to this. Let's try this again. Okay. Let's see what we got here. Okay, divided by 16 is this. Like that. It's 2.37. Where did I make a mistake here? 10. T-value is A11. 2.5. Yeah, no, that's no good. Standard deviation. Oh, I forgot to divide by the square root of the sample size, didn't I? This is, no, did I include sample size? Sample size was up there. No, I made a mistake here somewhere. Well, I'll work it out before our next session. But the reason why I know I made a mistake there is because when I do it with SPSS, I wind up with a standard deviation. Yeah, I definitely forgot to divide by square root of n somewhere here, right? So my standard deviation was similar in the 2 of these. We calculated this before, and I just want to resolve this before I move on. Okay, where is my document? T-test variations. Got something here. Oh, I need to, oh my goodness, how dumb. Okay, here we go. So we want the bottom of this equation. So we calculated our pooled standard deviation, and our pooled standard deviation was equal to, and we didn't finish it, did we? Our pooled standard deviation was equal to, so let's see, C5. Okay, this is, let's see, divided by square root. That's our pooled standard deviation. But the bottom of this is equal to, should be equal to our pooled standard deviation times the square root of, I'm going to put an asterisk in there, times the square root of 1/9 plus 1/9. Forgot that. And let me close parentheses. Okay, and hit enter, and it's 1.19. Okay, so the difference between our 2 means, okay, A11 minus B11, the difference of 2 means divided by 1.11. And our T value is 2.18. These 2 means are 2.18 standard errors apart. Okay, 2.18 standard errors apart. Sometimes you make a mistake, you learn a little bit more. Right? 2.18 standard errors apart, in which case it's greater than T critical, which was 2.12. So we can reject the null hypothesis and reject that mean for males equal to mean for females, and accept the alternative hypothesis that the mean for females is different than the mean for males. Okay, so our T value is greater than T critical. And when we did our t-test using SPSS, here we go. Let's see what happened. Okay, I'm going to go across, assuming equal variances, Top line is when you assume equal variances, because this is now two sample t-tests or independent samples. The bottom line is if you don't assume equal variances. Our rule suggested that if the standard deviations of the two groups are not double the other, we would use the top line. So that's our rough rule. So let's use the top line. We see the t-value is 2.184, similar to what we just calculated, 16 degrees of freedom. And the probability that we would get this big a difference if the null hypothesis was true is only 4%. So since the probability we get this extreme of value, a difference between the two means, is less than 5%, we reject the null hypothesis that the two means are equal and accept the alternative hypothesis. Okay, now let's take another look back here at the test for equality of variances. There's a kind of very thin line, might be hard to see on your monitors, but you'll see it when you run this on your own version of SPSS. If I look at that thin line over here, it separates two parts. The part on the left is the actual t-test. On the right is the actual t-test. The part to the left is actually a test for equality of variances. This test assumes the same way as we did before, null hypothesis, where the variances are equal to one another. So in other words, we're going to stick with the top row unless there's less than a 5% chance that they're unequal. Okay, so equal variance is assumed. If this is greater than 0.05, we'll stay here. If it's less than 0.05, we'll reject the idea that the variances are equal and accept the alternative and use the bottom row. So in this case, we stuck with the top. Our rough judgment of one standard deviation, not twice the other, agrees with this test. So we use the top line instead, okay? And we reject our null hypothesis. I hope I didn't confuse you too much there. But hopefully, going back over it was a little bit of an education as to how easy it is to omit one of the steps in this whole thing and why SPSS is such a wonderful tool for calculating these things. Now, I want to do one other problem, and that is, let me just get to it here. I'm going to hold off on paired samples until next week, but I want to do one more problem here, and that is, oh, by the way, you have this sheet which summarizes all these formulas if you want to do them manually for equal variances assumed, unequal variances, for proportions, comparing two population proportions, and next week we're going to look at separate from this. I didn't include single sample t-test because it's very simple, and also paired sample t-test, which next week we're going to see is really just another version of single sample t-test. So don't worry about that. This procedure will help you if you need to ever do this manually. Hopefully, beyond what we did here, maybe one example on a homework assignment. It's unlikely that it would ask you to do this calculation for two sample t-tests manually. Instead, we'd get you to use SPSS, a tool that we have designed for that. So now, let's take a look at this other value, this other problem that we have. Second problem, the third problem we have is that we have a two sample t-test, right? A two sample t-test or hypothesis test, and we're comparing a population of males to population of females. We have a sample size of 9, just like we did before, except this time, let me open this one in Excel and see what that looks like. Okay, and let me see if we can get to it. Okay, okay, this is going to be this example. I'll get it opened in Excel. Okay, this time in Excel, let me calculate what the standard deviation of these two groups is. Of this group, males, is 2.37, and for females is 1.10. So in this case, the standard deviation of these two groups is so different that I'm going to instead use the formulas for unequal variances rather than equal variances. Well, fortunately, we have this as a SPSS file, which I'll open now. Say open data, navigate to my desktop to sample t-test unequal variances, and open this up, and we'll have the same data in front of us in a new window, and we can see this is the same data as we had before. And I'm going to say analyze. I'm going to say compare means again, right? Simple as can be. Compare means except, and it's an independent samples t-test. So far, we've looked at one sample t-test, an independent, or in other words, two sample t-tests. Okay, I'm going to put the values, the actual variables with the values. Marguerite, I'm gonna look at what you just typed there in just a second. I just want to get this set up. And I'm going to take gender, I'm going to move it into the grouping variable. I believe it's still 1s and 2s. And I'm going to hit continue and OK. SPSS is going to create a new t-score. Notice the output window just keeps adding to the bottom so that we can save all of our results. Okay, and in this case, the t-score, well, first of all, let's decide whether we want to, if we looked at the standard deviation, we would say, I probably want to assume unequal variances. And in fact, if you do look at this, you say to yourself, okay, let's assume unequal variances. Okay, but should I do that? Well, if I look at equal variances assumed, the significance for that null hypothesis is 0.01. It's less than 5%. So that would lead me to reject that null hypothesis and use the bottom line, equal variances, not assumed, my alternative. Okay, and in that case, the t-score is 2.51, okay, similar to what we calculated before. And the degrees of freedom is 10 point. If you look at the formula for degrees of freedom, it's pretty complicated, so that's why it comes out so odd. But the important part, the probability that we would get this extreme of value for t if the null hypothesis was true is less than 5%. So therefore, again, we reject the null hypothesis that the mean for males is equal to the mean for females in this example. Okay, so now let me see what we have here. Okay, I got 2.38. Oh yeah, you got a better answer than I did. Forget the z-score question. It was just from the table. I'm not sure which one that was. Z-scores for 90. How do you get? Oh yeah, the z-scores. The critical values of z that I did in the earlier problems was strictly from the table. Exactly, using the degrees of freedom to decide. In fact, you could do that here. You could say that the degrees of freedom is about 10. You could go to the table, look up what that is, and I'm just going to guess and say it's like something like 2.3 or 2.4. So t exceeds that. So you could reject it just by looking at this and the table, or you could just, why bother when SPSS actually calculates the exact probability for you. So you can take a look at that directly and see what the likelihood is that you would be wrong if you reject the null hypothesis, or more correctly from a statistical analysis, statistical perspective, what's the likelihood that you get that big a difference in the two means if the null hypothesis was true? And there's only a 3% chance of that happening. So you feel comfortable rejecting the null hypothesis. And Marguerite, good work on Marguerite. I think it looks like you did the one that I got wrong, right? And I'm glad you did that. I love when people catch my mistake. I only wish that you had typed that in there before I went off on a tangent there for so long. Okay, good work.